All right, so we just left off, right, talking about how we're going to find our cheapest possible option out of everything on or above our isoquants, and we got to a very familiar place, right? We needed to compare the slope of our isoquant with the slope of our isocost curve, equivalently to comparing the slope of our budget constraint to the slope of our difference curve. So what we have to do now is think about what those slopes are going to be and what they tell us, right? So we can make intuitive sense of these graphical conditions. So to start with, let's think about the slope of our isoquant. So what our isoquant is doing, right, just to remind ourselves, I'm just going to draw a bad one here. Right, our isoquant is telling us all of the combinations of labor and capital that produce the same amount of output, right? So if we're thinking about the slope of this line, it's going to be, right, what's the change in capital per change in labor that produces the same level of output, right? In other words, if we wanted to increase our use of labor, or let's say decrease our use of labor by a unit, right, how many units would we have to increase our capital? So if we're thinking about this on the margin, what we can say is our change in capital times the change in output that results from a change in capital plus the change in labor times change in output that results from a change in labor, right, has to equal 0. Change in capital times the marginal product of capital plus the change in labor times the marginal product of labor has to equal 0, right? Equivalently, of course, dk times the marginal product of capital is going to equal negative dl times the marginal product of labor. So if we want to know what's the change in capital per change in labor, that's just going to be dk over dl is going to equal df of lk dl over df of lk dk. Negative. So this should look really, really familiar, right? What we're saying is the amount of capital that we'd have to hire in order to fire a worker without changing our output is going to be the marginal product of labor divided by the marginal product of capital, right? Why does this make sense? The more productive a worker is, the more capital it's going to take to replace that worker. The more productive capital is, the less capital it's going to take to replace that worker, right? So this is going to look like, and remind you of the marginal rate of substitution. We're going to call this our marginal rate of technical substitution, or technological substitution, right? So our MRTS of L and K is going to equal this thing, right? dF dL over dF dk. What's our MRTS going to tell us? It's going to tell us the amount of capital we need to replace a little bit of labor, right? The amount of capital per unit labor we need. Amount of K needed to replace a unit of labor, right? Really the ratio, right? The infinitesimal amount of capital it takes to replace an infinitesimal bit of labor. Awesome, awesome, awesome. Right, now the reason I'm talking about this in terms of how much capital you have to hire to give up a little bit of labor is because, remember, we're thinking from the perspective of the plant manager. Ideally, you'd fire everyone and get rid of all your machines, right, to save yourself as much money as possible. You're stuck hiring people and then hiring machines because you're trying to produce output. So you're happy when you have less labor. You're sad when you have to bring on more capital. Cool. So this is the slope of the isoquant, right? So let's switch over to thinking about the slope of the isocost. So remember, right, the isocost curves are straight lines like this, right, that tell us right, of all the combinations of labor and capital that cost the same amount of money, right? So the slope of this thing should be basically the amount of capital. If we think about the slope of this thing, it's going to tell us something like the amount of capital that you would be willing to take in order to fire a worker, right? The number of units of labor you'd be willing to hire, or sorry, the units of the machines you're willing to hire in order to fire somebody, right? The reason you want to fire the person is to save the money. The reason you're unwilling to hire more machines is because they cost you money, right? So the slope of our ISO cost curve, right? How happy are you when you give up a unit of labor? It's going to be the wage rate W, right? How sad are you when you have to hire an extra machine? It's going to be the rental rate R. So the same way that we had a budget constraint, right, that had a slope that would be the price of labor over the price of capital, right? That's going to be the slope of our ISO cost curve. Price of labor is just the wage. Price of capital is R. So the slope of our ISO cost curve is just going to be equal to the wage rate over the rental rate. And it means how much capital are you willing to hire to fire a worker. Right? So when workers are really expensive, when wages are really high, you're willing to hire more capital to get rid of a worker. When capital is really expensive, right, you're willing to hire less capital to get rid of a worker. Awesome. So now that we know what the slope of our ISO cost and the slope of our ISO quants are and what they mean, let's think through how to solve interior and corner solutions. So let's start with interior solutions. Let's go back to the problem we started with, right, where we had a nice, beautiful isoquant like this, Q equals 4, and we had nice, beautiful ISO cost curves like this, right? We're looking for this optimal point, right, where we're going to have the slope of our isoquant, right, in other words, our MRTS, equal to the ratio of wage to rental rate, and where we're producing 4 units of output, right? We had the production function, f of L k equals L to 1/2 times k to the 1/2. We had a wage rate of 20. We had a rental rate of 5. Right? So we're going to have 2 conditions, just like the 2 interior solution conditions we're used to. 1, MRTS, L and K has to equal the cost ratio, right? And then 2 is going to be satisfy, basically produce enough output. I'll say satisfy isoquant, produce enough output. Right, because remember that the isoquant is our new budget constraint, so plugging our solution here into our budget constraint is going to mean plugging it into our isoquant equation. Cool. So let's start here, the MRTS. So our MRTS, right, is going to be dF dL over dF dk. So we just need these 2 partial derivatives, then we're good, right? So dF dL is going to be, right, the derivative of L to the 1/2 times k to the 1/2 with respect to L, treating k as a constant. So it's just going to be 1/2 L to the minus 1/2 times k to the 1/2, right? dF dk is going to equal, for the same reasons, 1/2 L to the 1/2 times k to the minus 1/2. Right? So if I take one over the other, I can basically bring the minus 1/2 down, bring the minus 1/2 out, right? Then 1/2s cancel, so I'm just going to get k over L. Right? Again, we can do a gut check here. If we have more capital, that should make capital less productive and labor more productive. So we'd be willing to give up more units of capital to get a little bit of labor. If we have more labor, that makes capital more productive, labor less productive. So we should be willing to give up less capital to get a little more labor. Awesome, awesome, awesome. So now we just need to set K over L equal to W over R, right? Which is of course equal to 20 over 5. Or if you prefer, 20 over 5 is just 4. So I can say K equals 4L. Nice. So what do I do with this? Well, I plug it into my isoquant. Right? So remember, my isoquant is going to be L to the 1/2 times K to the 1/2 has to equal 4, or really be greater than or equal to 4. So I'll just stick 4L in for K and say L to the 1/2 times 4L to the 1/2 greater than or equal to 4, right? This thing here I can break apart. I can distribute the 1/2. So I'll say L to the 1/2 times 4 to the 1/2 is 2. L to the 1/2 is L to the 1/2 greater than or equal, or I'll just say equal to 4. Yeah, this should really be equal because, of course, we're satisfying it with equality. So then I'll just say L equals 4 over 2 equals 2, right? Now that I know how much labor I need, I can just use K equals 4L, right? So K is going to equal 8. So what's this telling me? It's telling me the cheapest way for me to produce 4 pounds of potatoes, 4 tons of potatoes, is with 2 workers and 8 machines. Why does this make sense? Because workers are more expensive than machines. So in order to have my cost ratio equal my Mrts, right, I must end up using more machines than I use workers. All right, awesome, awesome, awesome. So this is how we attack interior solutions, right? Much the same way that we attacked interior solutions with consumer optimization problems. One more thing I want to point out, though, that is a little bit different from consumer optimization problems, is what happens when we have a change in input prices. So as you might remember, right, when we had consumer problems, I had a budget constraint, let's say chocolate and bananas, right? If chocolate got more expensive, I would go from a budget like this to a budget like this, right? My budget constraint would shift inward. So what's the picture going to look like if instead I have a change in input prices? Let's say, for example, that I have R equal to 20, right? So W equal to 20 and R equal to 20. The natural thing to think, right, is that I would say, well, I can't afford as much capital anymore, so I'm going to have some new ISO cost curve like this. But importantly, right, if we had some new ISO cost curve like this, this would be insufficient, right? This would be too cheap to produce the amount of output that we need. So our optimal choice is still going to be on the same isoquant. It's just going to be on a different slope, right? So essentially, as the input prices change, we rotate along our isoquant, right? If capital got even cheaper, we would just rotate even further. Cool, cool, cool. Okay, great. So now let's talk about corner solutions. So we can't talk about corner solutions using the motivating example we set up, right? K to the 1/2 times L to the 1/2, because Cobb-Douglas production functions, just like Cobb-Douglas utility functions, don't have corners, right? In other words, if I have 0 capital or 0 labor, I don't produce anything. So that's never going to be optimal. So instead of doing that, let's just draw a picture and think. So I have an isoquant that looks like this, right? This is intended to be a little bit bendy, but not terribly bendy, right, for L and K. I'll have a corner solution, right, a vertical corner solution, graphically, if I have a price ratio like this, right? That would be a vertical corner. And I'll have a horizontal corner if I have some isoquant like that, right? It's clear that both of these are solutions because everything cheaper is not going to produce enough output. Likewise here, everything cheaper is not going to produce enough output. So, okay, so that makes sense graphically. Let's make sense of these two conditions. So we have a vertical corner. Right, we can just see, looking at this graph, that we must have a cost ratio that is steeper than our MRTS. Right, we must have MRTS less than or equal to our blue cost ratio. Right? Otherwise, our ISO cost curve would go above our MRTS. I mean, go above our ISO quant, right? There'd be something better. So why does this make sense? Well, our MRTS is the amount of capital you need to replace a worker, right? Which is going to be less than or equal to K you're willing to hire to replace a worker. So what's this saying? It's saying that if the amount of capital you need to replace a worker, right, is less than the amount of capital that you're willing to pay to replace a worker, then it makes sense that you've replaced all your workers, right? You've got one of these dark factories that doesn't have anyone working at it, right? It's just churning out output with machines. Cool. Robot apocalypse, right? So how about the other corner? How about the horizontal corner? Well, the horizontal corner, it's clear graphically, right, that we're going to have an MRTS that's got to be steeper than our price ratio. Right? And why does it make sense that we'd hire only workers when our MRTS is steeper than our price ratio? Because that tells us that the capital you need to replace a worker, right, is less is greater than the capital you're willing to hire to replace a worker. Right? In other words, right, I would, in order to get rid of a worker, I would need to hire something like 2 machines. I'm only willing to hire 1 machine to get rid of a worker, right? Otherwise, it's more expensive than just keeping the worker. So I get rid of all my machines. I only have workers, right? I have, interpretive dance troupe or something that doesn't require any capital at all. Awesome. So there we go. What we've done so far is we've effectively solved our plant manager's problem, right? We know if we're a manager of a production technology, we know the technology and we know our costs, we're going to be able to use these tools, right, finding interior and corner solutions, to tell us how to produce any given amount of output as cheaply as possible. So what we're going to do next is essentially use that information, use that problem-solving process in a similar way that we used consumer optimization problems to make demand curves. So essentially what we're going to do is we're going to say, if what we've done so far is said, when you get a call from the CEO saying, I want 20,000 Honda Civics, we're going to do the opposite of being able to tell the CEO how much would it cost to make any given amount of output, right? So that that information is available when you're choosing how much to consume. In other words, we're going to learn how to devise cost functions from production technologies and input costs.